Hey Pre-Calc, welcome back. Hope y'all are well. Our objective today is going to be to apply the counting principle. We are starting a section called combinatorics, so it's a little bit of an intro to statistics. I've got the checklist on the screen. You know what to do from here. All right, you don't need to you don't need to write anything yet. First, let's just talk about, we've got these three people and these three emojis. How many different ways, how many unique ways can we order these three people? So we've definitely got the one order that we have here, right? We'll call it love, wink, excited, right? Let's say that we keep love where it is, and let's switch excited and wink. There's another order, right? Now, that's all we can, that's all we have if we keep love first, correct? Another way would be to do, let's have wink go first, and that would give us love here, excited here. We could also do wink first and switch where excited and love go, right? And that's it for having wink go first, right? The last option for who goes first would be excited. And I could go like love, then wink. Or my other option for having excited be first would be wink. Then, whoops, sorry. I said wink. Wink, then love, right? So how many different possibilities? We've got 6 different possibilities here, right? And so what I want you to think about is there are essentially 3 slots, right? For this first slot, how many possibilities do I have if I haven't changed anything yet? We've got 3 possibilities, right? We could either have love in the first slot, wink, or excited. Now, once that first slot is filled, how many people are left to choose from? Just 2, right? So there are 2 possibilities for that second slot. And once that second slot is filled, there is only 1 possibility for that third slot. And if I multiply all these together, it's called the counting principle, 3 times 2 times 1, I get 6, right? Another way we write 3 times 2 times 1 is called 3 factorial, okay? So look, it's an exclamation point, but in math it's called a factorial, and this is 3 times 2 times 1. 5 factorial would be 5 times 4 times 3 times 2 times 1, okay? So let's take a look at the definition we were just kind of intuitively looking. So let's formalize. You don't need to write this down, but the total number of outcomes for an event is found by multiplying the number of choices for each stage of the event. Just like last time, we had 3 stages. For the first stage, we had 3 choices. The second stage, then we only had 2 choices. And the last stage, we had 1 choice, which again is 3 factorial, which is 6. If you want to find your factorial button on like an 84, like if I wanted to do 3 factorial, I can go, I don't know why it does that, it messes up on us, 3, and then you're going to go math right under the green button, scroll over to probability, P-R-O-B, and it's number 4, that factorial, that little exclamation point, we should get 6, right? And here's our next definition, that the number of ways that a set of n objects can be arranged in order is n factorial. First pause on the screen, go ahead and copy as much as you need to. For example 1, hit continue when you're ready to continue. So example 1 says, if ice cream sundaes come in 5 possible flavors with 4 possible toppings, how many different sundaes can be made with 1 flavor of ice cream and 1 topping? So how many, quote, events would you say we have? We have 2 events because we can have 1 flavor of ice cream and 1 topping. Okay, so how many different possible flavors do we have? We have 5 flavors, and how many different toppings do we have? We've got 4 toppings, and so the counting principle says multiply those together. You've got 20 possible different combinations. First pause on the screen, go ahead and copy what you need to for example 2. So example 2 says, how many different passwords can you make on an iPhone? And there are 10 digits to choose from, and your password needs 6 digits, okay? So first we say, how many events do we have? Well, there's 6 different digits we need, right? So I've got 6 slots. Okay, how many different possibilities, how many different choices do I have for the first slot? I've got 10, right? I've got 10 options for that first slot. How many for the second? Still 10, right? Because I'm allowed for numbers to repeat. If I choose 1 here, I can still choose 1 for my second slot. And I have 10 for each slot, right? So this is 10 to the 6th, which is 1 with 6 zeros, right? So how many different combinations? 1,000,000. And force pause on the screen, go ahead and read example 3. Hit continue when you're ready to work it together. So we've got this license plate, and let's say there are 2 options. The first option is there's no restriction on whether the letters or numbers, on the letters or digits that can be used. So we know that there's how many events? There's 6 events. There's going to be 3, the first 3 are letters, right? And the next 3 are digits 0 through 9, okay? And for part A, we say there's no restriction. So how many letters in the alphabet? 26. So I have 26 possibilities for that first slot, that first event. How many for the next one? Still 26, right? And still 26 for this slot. Okay, now when I move over to the next 3 parts of the license plate, they all have to be digits. How many possible digits do we have? We have 10. So 10 possibilities for this event, as well as the 5th and 6th events as well. So if you multiply all of that together, you get 17,576,000 different combinations for these license plates. Okay, let's try the same thing, but this time let's say no letter or digit can be repeated, okay? So if I use A for that first slot, I can't use it for the second or third slot either, all right? So I still have 6 events. The first 3 are letters. The next 3 are digits. So for that first slot, I still have 26 options, right? Because I have 26 letters. Now, how many options for that second slot? Only 25, because whatever letter I used here, I can't use here, but any of the others work. And what about for that next slot? 24 options, right? Okay, moving on to my digits, I've got how many digits to begin with? So 10 for this event. How many for this next one? Just 9, and then 8. We can see for sure it's going to be a smaller number than what we got in part A, which makes sense, right? Because we don't have as many values to work with. So what I got was 11,232,000. So still quite a few different possibilities to play with for license plates. All right, first pause on the screen, go ahead and read example 4. Hit continue when you're ready to work it together. All right, so example 4, we would know, we want to count the number of different 9-letter words in quotes because they don't actually have to be real words. Just basically, how many different ways can I rearrange these letters, okay? So for dragonfly, do you have any repeat? No. And there are 9 different slots, right? So for that first event, there's 9 events. There are 9 options. That second event, well, you've used 1, so we will only have 8 options, and then 7, and so on and so forth. So for part A, since you have no repeats, it's just going to be 9 factorial, and if we do that in the calculator, it'll be 9 math, scroll over to probability number 4. So 880, sorry. And by the way, you can do this in Desmos as well. Just do 9, literally exclamation point, and I'll give it to you right here. All right, so for part B, I still want to rearrange these 9 letters. What do you notice is different about part B? Yeah, you've got this repeat. You've got T repeating once, right? It appears twice. So I'm still going to start with 9 factorial. However, I'm going to need to divide out how many different ways I can rearrange 2 T's. Well, that would be 2 factorial. 2 factorial is 2 times 1, which is just 2. So I can really just take my answer I got earlier and divide by 2, which is going to give me 181,440. All right, let's try part C. So I've got 9 letters, still 9 events, so I'm still going to do 9 factorial. But now let's take a look at our repeats. Let's see. B repeats 1, 2, you've got B 3 times. So I'm going to need to divide out, how many different ways can I arrange B's? 3 times 2 times 1, because there's 3 of them, so that's, I need to divide out by 3 factorial for that, because they're not going to give me anything new, so I need to divide those possibilities out. And let's see, what else repeats? Our E's repeat, right? They repeat, there's 1, 2, 3 of those as well, so I need 3 factorial there as well. So let me grab a fraction here. So I'm going to go 9. Whoops, try that again, 9 factorial over 3 factorial, which is 6, times another 3 factorial, which is 6 again. So this time I'm only getting 10,080. All right, you all, that is all we have for today. I will see you next time.